Okay, for the longest time, brain-computer interfaces, or BCIs, felt like something straight out of science fiction, right? Well, that era is over. The tech is actually here. But it turns out the real fight has totally shifted. It's not about the initial wow factor of inventing it anymore. It's about something way harder, execution. It's about taking these incredible demos and making them work for real people in the real world. So let's get into it. And this is why it all matters so much. We're not just talking about controlling a cursor on a screen. This quote is from an actual patient using this technology. It's about giving someone back their voice, restoring a connection that was lost. This is the human side of it, and it's the engine driving this entire field.
So yeah, the dream of mind control, it's happening. You've got companies like Neuralink making it possible for paralyzed patients to use computers just by thinking. And that's a huge deal. But this amazing progress has also shined a massive spotlight on a fundamental roadblock.
And that roadblock, well, it's this huge, high-stakes dilemma that has basically been holding back the entire BCI field for decades. It's a forced choice that every scientist and every company has had to face. So here's the deal, the essential trade-off. On one side, you have invasive implants, surgically put into the brain. They give you absolutely incredible performance. On the other side, you've got non-invasive EEG caps that you just wear. They're totally safe, but honestly, the performance has been painfully slow and super unreliable. So you could have performance, or you could have safety. You had to pick one. You couldn't have both. And when we talk about high performance with the invasive stuff, we really mean it. This is the gold standard. I mean, by listening right at the source, to the neurons themselves, these systems let people type at 90 characters a minute, just by thinking, and even restore speech at 62 words per minute. The signal is just crystal clear. But it comes with a massive, massive catch. And here's that catch. This quote just nails the problem. To get that amazing high-fidelity signal, you need a craniotomy. That's open brain surgery. The risks, the cost, the recovery, it all means this incredible technology is stuck in these tiny clinical trials. It's super powerful, but it's just not something you can give to everyone who needs it.
So you might be asking, why not just use the safe cap then? Well, here's why. Think of your skull and your skin like a thick, foggy window. The brain's electrical signals have to pass through that fog, and they get all smeared and muffled along the way. Engineers call this a low signal-to-noise ratio. It's like trying to hear someone whisper across a crowded, noisy room. The signal you want is just buried in static.
And here's what's so frustrating about that static. For a huge slice of the population, we're talking up to 30%, it's so noisy that the device just doesn't work at all. It's a phenomenon called BCI illiteracy, and it's the reason that this safe, non-invasive technology has always been more of a cool idea than a practical tool. Well, until now.
So you've got this impossible problem, right? A team at UCLA looked at it and decided to flip the whole thing on its head. They said, what if we stop trying to build better hardware to get a cleaner signal, and instead, what if we just build smarter software to understand the messy signal we already have? And their big idea is this concept called shared autonomy. Honestly, the best way to get it is to think about the lane keep assist feature in a modern car. You're the driver, and you give the high-level goal, which is just, hey, stay in this lane. But the car's AI is handling the hundreds of tiny, constant steering adjustments to keep you perfectly centered. The human and the AI work together as a team. Okay, so here's how the magic works. The user just thinks a rough thought, something like, I want to move that thing over there. The EEG cap picks up that messy, noisy signal as usual. But, and this is the secret sauce, a camera is also watching the scene and an AI sees what's on the table. The AI then brilliantly blends the user's fuzzy brain signal with the hard facts of what it sees in the room to figure out the user's real goal and then execute it perfectly.
And did it work? Oh yeah. The results were just staggering. On average, this AI copilot made users almost 4 times faster. Things that were clunky and difficult suddenly felt smooth and easy. But the truly mind-blowing result came when they tested it with a patient living with paralysis.
This, right here, is the game changer. When they asked the paralyzed participant to do a complex task with a robotic arm using the normal BCI, he couldn't do it. His success rate was 0. It was literally impossible for him. But then, they turned on the AI copilot, and his success rate jumped to 100%. The AI wasn't just making him faster, It was making the impossible possible. It turned a lab experiment into a tool that actually works. So while the UCLA team was cracking the code on the software side, a company called Synchron was attacking the exact same dilemma, but from a totally different angle, the hardware. They came up with a whole new way to get a clean signal from the brain without all the risk of major surgery. This is the stent road, and its big innovation is that it gets to the brain without ever breaking the skull. Instead of drilling, it travels along the body's own natural superhighways, your blood vessels. The whole procedure is what they call minimally invasive. They make a small incision in the neck, enter the jugular vein, and then carefully guide a catheter all the way up into the brain to a blood vessel right on top of the motor cortex. Once it's in place, this little mesh-like stentrode expands, pressing against the vessel wall, getting it close enough to eavesdrop on the brain's activity. And check this out. This is the really clever part. Over the next 3 months, the body doesn't reject it. It accepts it. The body's own cells actually grow over the device, making it part of the blood vessel wall. One expert even compared it to getting a tattoo. It just becomes a part of you. And that dramatically lowers the long-term health risks. So what does it all mean when you put these pieces together? You've got smarter software that can finally make sense of noisy signals, and you've got smarter hardware that can get a clean signal without open brain surgery. What you have is a completely new era for brain-computer interfaces. The entire conversation in the BCI world is changing. For decades, the question was just, can we even do this? And now, the answer is a resounding yes. The new question, the much harder, grittier question, is all about execution. It's how do we make this safe, reliable, and accessible for the millions of people who could actually use it? And this really lays out the 3 distinct paths forward. You've got the super high-risk, high-reward approach like Neuralink. You've got the AI-powered software solution that finally makes the safe tech usable. And then you've got this clever, minimally invasive middle ground from Synchron. But here's the thing. Whenever you solve big technical problems, you almost always create new challenges. And this might be the biggest new challenge of all. By creating these amazing solutions, especially that AI copilot, we've stumbled into a really thorny ethical problem. It all comes down to a simple question. Who's really in control here? Is it the person or is it the algorithm? I mean, really think about that for a second. The whole system is built on the AI making an educated guess, an inference about what you want to do. But what happens if it guesses wrong? If your will and the machine's prediction don't line up, this amazing tool that was meant to be liberating could suddenly feel like a new kind of prison. So here's the bottom line. For half a century, the challenge was purely technical. Can we just read the brain's signals? That era is ending. The new frontier, the defining question for the next 50 years, is going to be an ethical one. As we learn to interpret these signals, how do we make sure we're building tools that truly empower people instead of taking away their agency?